Good day, concrete lovers. My name is Tyler Lay, and now I'm going to compare different types of SCMs. This is going to be a review video, but sometimes reviewing helps you see things in new ways and helps you look at things differently. So our goal today is to compare SCMs, all the different SCMs to one another, and how they affect the properties of concrete, and then compare that to Portland cement. This chart or table actually compares the chemistry, the oxide content of the different SCMs that we've been talking about. There's the fly ash, class F versus class C. There's slag, silica fume, and Portland cement. And you can notice that they're pretty different. Class F and class C ashes are pretty different from one another. Slag's different. Silica fume's almost pure SiO2. Okay? And then there's good old Portland cement. This gives you the pozzolanic reactivity of the material. And it's got this sitting in the center between these two, but that's not quite right. This should be closer to the class F, and the class C would have a lot lower pozzolanic activity. This is how much calcium hydroxide does it react with per gram of material. Here's slag. It's got a moderate pozzolanic activity. Silica fume's a little bit higher, and Portland cement's got nothing, right? Here are the particle sizes, and you can see that the fly ash and the slag and the Portland cement are all similar to one another. But again, the silica fume is about 200 times smaller than any of them. It's crazy, right? Here's the surface area. Again, these are similar to Portland cement, but remember, because fly ash is spherical, it helps concrete flow better. Slag particles, it says, are irregular, but that's better than angular. Angular is like ellipsoid, and it doesn't do as good a job flowing and moving. And silica fume particles are spherical. I showed you an image of them before, but they're so small. Look at their surface area. This is their surface area per kilogram of material. That's insane. That's so massive. And that's why they are so poor for the workability of the concrete. And we'll talk more about that coming up. Now, another way to think about these SCMs is on this ternary diagram. A ternary diagram is a way to show three different chemical components of different materials. For example, if we took the oxide content that I was talking about before and I plotted the different SCMs on this chart, it would tell you something. Silica fume is pure up here at SiO2. Okay, class F fly ash is closer to SiO2, but it's got some aluminum in it. It doesn't have as much calcium in it. Class C fly ashes are right next to it. It has more calcium in it. Slag has even more calcium, and then we have good old Portland cement down here at the bottom. And this chart's, these lines are really important. These lines show, and they're approximate, okay? They're not perfect. These lines basically show anything over here is more pozzolanic, and everything over here is more of a hydraulic cement. Okay? And there's some of that slag should be in there. Some of it should be in there as well. So there's certain regions in here where we've got blends. We've got material that are both a pozzolan and a hydraulic cement, both. Then we have some that are more pozzolan, and then we have some that are more hydraulic cement. So that gives you some kind of insight. And remember, pozzolans take a long time, sometimes months, to really see their benefits, and they react with the calcium hydroxide. And the hydraulic cements, they react earlier, okay? They react earlier. So I said, why are pozzolans so beneficial to concrete? And why are secondary cements so beneficial to concrete? Well, when it comes to property-wise, the pozzolans are great because they consume your calcium hydroxide, the stuff that you don't really need. I mean, I call it the human shield of concrete, right? You don't need it as much. You can lose some of it just fine, no problems, and produce more of the good stuff, CSH. And remember, when these things form, whether it's the pozzolan or the secondary cementitious material, the structure from the OPC is already there. It's already there. And so they form where they're needed in the open space to help block things up, give it more strength, make it less permeable. It's a good thing. So we're going to move on with the comparisons. And it's a great way to compare something new to something that you already know something about. So we're going to compare all of these SCMs in a kind of a more quantitative manner, not quite super quantitative, but getting closer to quantitative manner in comparison to Portland cement. And we're going to remove Portland cement. That's the way it's typically done. You remove a certain percentage of Portland cement and you add in the SCM as a replacement. And we're going to use all of these at their typical replacement level that they're used in industry, okay? And we're going to give a relative ranking and discuss why this ranking occurs. And this is a modified approach. This stuff I'm about to show you is modified. It was first done and thought of by Thomas and Wilson in 2002 when they were making a document about fly ash. I'm going to use a relative ranking, okay? And I'm going to say when something goes down, it reduces it by less than 20%. Maybe not 20%, but not more than 20%. And if I give something a double down, 2 arrows down, that means it's going to significantly reduce it. And it's going to reduce it between 20 and 40%. An arrow up means it increases it by about 20%. Actually, that shouldn't be greater than. That should also be less than 20%. And if it's a double up arrow, then that's going to be 20 to 40%. So that's going to be much more of a increase. And then our dash line here is going to mean no change, as in it doesn't do anything different. And if I use an up and down line, it means the effect varies. It means sometimes it may go up, sometimes it may go down. It just depends. And then the good old question mark. The question mark means we don't have much data and we need to learn more. And just trying to be honest with you. So we're going to compare all these mixtures on a flowable concrete. One that maybe have like a 6-inch to 7-inch slump. Something that would be used for a slab on grade or for a bridge deck. Something that might be pumped. And we're going to assume that our SCM is being replaced at this level. Class F and Class C, 20% replacement of Portland cement. Slag's going to be replaced at 35%, and silica fume is going to be at 5%. Now, these are not necessarily gold standards in the industry. Sometimes they go higher, sometimes they go lower, but these are good middle of the road. Everyone pretty much agrees that this is just fine and not any issues. But slags, you can go up to 50% replacement. Class C, 40% sometimes, and Class F, 30% sometimes. Silica fume, people would like to go more, but it just gets sticky. I've seen 8% before, but you really can't do much more than that. In this first chart, I'm going to compare the fresh properties of all these different materials, the fresh properties of these SCMs. And I'm going to be talking, so I've got my SCMs over here, Class F, Class C, slag, silica fume. And at the top, I have slump. You guys know what slump is, right? Workability. Bleeding, that's how much water is coming up to the surface of the concrete. Heat of hydration, how much heat is given off as it reacts. Setting time, how long does it take before initial and final set? How much time does it take before concrete starts to initially harden? And then plastic shrinkage cracking. That's where, when the concrete is setting, if it dries too much at the surface, it can actually shrink and crack. I'm going to talk about each one of these properties, and then I'm going to go down how every one of these SCMs affect that property. Let's start out with slump. In the upper left-hand corner, I'm going to write whether it's up, down, double down. You can look back at the previous page to see what that means. But with class F fly ash, it's going to help increase slump. And now I'm going to write down why. Why is really important. You need to understand, always try to understand why something happens. Your slump is going to go up because we've got spherical particles. And they're similar in size, similar to OPC in size. I don't mind writing in the class C box because it's the same thing with the same answer. Now let's talk about our friend slag. Slag, we have a neither. That means it doesn't really increase it. I mean, it's about the same. And the reason why is that they're similar in size. To OPC and shape. Now let's talk about silica fume. Silica fume, it's going to make your slump go way, way down. And why? Because they're fine particles. And there's so many of them. So I'm going to say lots. Lots of fine particles. Now let's move over to our friend bleeding. Bleeding is how much surface water comes up. And this is going to be the same. It will bleed more than OPC. Okay? And it's for the same reason. Same exact reason. Same. And then class C ash. It's going to do the same thing. It's going to bleed more. And also, same reason. And slag is going to have about the same performance as slump. Again, for the same reason. And then bleeding is going to go way, way down on silica fume. And again, it's for the same reason. So this water, instead of being able to come up to the surface, it's going to be absorbed on these itty bitty small particles. So it's not going to bleed as much. Now let's talk about heat of hydration. And we're going to first start out with our friend class F fly ash. And the heat of hydration is going to go down. Say, why is that? And the particles don't react. Remember, these class F fly ash particles are pozzolans, mainly. So they don't really do much reaction this early age time period. So they're kind of inert. So they're going to lower your heat of hydration a lot. With your class C, it's going to be, it could go up or it could go down. It could make your heat of hydration higher. It could make it lower. And it has, the reason why it has similar reactivity as OPC. But it's variable, right? It's variable. Could be lower, could be higher. Slags, your heat of hydration is going to go down. And the reason why is it's a slower reactivity. Than OPC. And silica fume doesn't have much impact at all because the particles don't react early on. They're pozzolans, remember? And it's used at a small volume. So silica fume is somewhat similar to Class F fly ash. There's just not as much of it. So let's move on to setting time. So your setting time's going to go up, and this is for the same reason. And here your setting time could vary, same reason. Setting time is going to go up. It's going to take it longer for slag to set up because it's got a slower reactivity than OPC. And setting time for your silica fume is about the same. And now we get to the final column, the plastic shrinkage. Now this is kind of a combination of setting time contributes to plastic shrinkage, but also how much water demand does the material have? How much water does it suck up? And I'm going to put a question mark on a lot of these because actually plastic shrinkage cracking is something that we don't have much data on. People don't really complain about it too much, though, in the field, so it's probably not a huge ordeal. But when it comes to silica fume, that's not the case. Sorry, it goes the other way. Silica fume, you have these fine particles that are not reactive. And they just suck up all your water. So they're just not that helpful for plastic shrinkage cracking. It's actually something you really got to watch out for if you're using silica fume. You need to fog your concrete. You need to really, really cure it well. It's kind of a big deal. Now let's talk about hardened properties. Okay? We have our favorite SCMs again. Class F fly ash, Class C fly ash, slag, and silica fume. And let's talk about early strength gain. And by early strength gain, I mean in the first 3 days. For Class F fly ash, what do we think? It's pozzolan. That means it's not going to react early. So this number is going to go down. Okay? And why is that? Because it's not as reactive. Class C fly ash could go up or down. Sometimes it's about the same as Portland cement. Sometimes it's a little bit higher. Sometimes it's a little bit lower. So it's similar reactivity to OPC, but variable. And then we have slag. Slag early age strength gain is lower. Okay? And again, it has a slower reactivity. It's not as bad as Class F fly ash. Not nearly as bad, but it's slower. Silica fume is going to have a much, much higher early age strength gain. And it's because there's small particles that pack well. All these small particles, they call it the wall effect. Put all these little small things in there and it's really hard to get things in, but it's really easy to transfer load, okay? And it also acts as a nucleating point. for hydration. All right. Let's talk about these long-term strength gain now. Now, the long-term strength gain is going to go up here. It's going to go up here. It's going to go up here. And it's going to go way up here. Why is that? Well, first of all, for Class C fly F ash, we have a pozzolanic reaction. Consumes the calcium hydroxide, forms more CSH, forms it in a structure that's more effective. Why does long-term strength gain go up for Class C fly ash? Well, the hydration products fill the existing pores. And that's also true down here for slags. That's why they're effective. And for silica fume, it's got a similar answer as this one. These really small particles, not only do they help with early age strength, they'll help with long-term strength as well. Now let's talk about fluid and ion penetration. These are going to all go down, 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 and double down. And the reasons are all the same reasons we talked about before. This pozzolanic reaction is going to form a tighter microstructure. These hydration products, when they form, are going to form in the pores that are already existing. Same thing for the slag, and that's going to help reduce fluid and ion penetration. And again, all these small little particles are going to help block and keep things out, going to keep your fluid and ion penetration. And really, when you can keep fluid out, then you're going to help out these alkali-silica reaction and sulfate attack. But there's even more. There's even more it can do. Class F fly ashes is a double down for ASR, okay? And it also, because it dilutes the cement, and it consumes calcium hydroxide. And that's going to lower the pore solution pH. That's going to actually help make sure your pore solution doesn't dissolve your aggregates as quickly. And for Class C fly ash, this is up or down. Sometimes it makes it better. Sometimes it actually makes it worse. And it's because it's similar to OPC, but variable. Slag is a double down, and one reason why is because you can dilute the cement with it. You can use it at a higher volume. Silica fume goes down because it makes it hard for moisture to enter. And now our friend sulfate attack, double down here, can go either way here, double down here, goes down here, and they're all the same reasons. So I hope this helped. I hope this kind of helped you compare and see how these different SCMs can work, how they change the properties, and it's really important to understand why. And why is where you should focus. What are the key properties of these SCMs then make them have the different properties. Then you won't have to memorize all these properties. You won't have to memorize all this up and down stuff. Keep thinking about the basics. Keep thinking about the basic properties, and then they'll all make sense from there. Take care.